Electric vehicles carry up to 800 volts. But you don't get a shock. Why? The answer is insulation. It prevents current from escaping the cable. A high-voltage cable has multiple layers. The conductor carries current. Insulation blocks it. Shielding controls interference. And the outer jacket protects everything. As long as current stays inside the conductor, there is no shock outside. But even a small crack in insulation can start a problem. Damage increases resistance, which creates heat and pushes the cable beyond safe limits. A tiny defect can lead to leakage. Leakage generates heat, and that leads to failure before you even notice. That's what happens inside the cable. But in the real world of 400 volt and 800 volt power distribution, a wire is never just a wire. Welcome back to Vidyut Tales. Today, we are going way beyond basic insulation to look at the massive engineering challenges of the high voltage harness, the nervous system of every electric vehicle. The cable itself is incredibly robust, but the exact point where it plugs into the high voltage junction box, the inverter, or the battery pack is where things get complicated. These connections are the weakest links. First, they have to survive extreme vehicle vibration without coming loose. That's why engineers use a CPA, or connector position assurance, a physical locking mechanism that guarantees the plug stays seated. Second, they need brutal environmental protection. We are talking IP6K 9K ratings, meaning these connectors are sealed tight enough to block out dust, road salt, and high-pressure water jets. But what if a mechanic accidentally unplugs a live cable, or a crash damages a connector? This is where active safety steps in, using something called an HVIL, the High Voltage Interlock Loop. Notice this tiny pilot wire running alongside the massive high voltage lines? It carries a low, safe voltage. The pins for this HVIL are physically shorter than the high voltage pins. If a connector is pulled out, this low voltage loop breaks first. In milliseconds, the vehicle's computer detects the broken loop and fires the contactors inside the battery pack, instantly killing the high voltage before the main pins even separate. It's an invisible safety net. Remember that metal braided layer from earlier? It's not just for physical strength. It's an electromagnetic shield. When the inverter chops up DC current into AC to drive the motor, it creates massive, high-frequency electrical noise. Without that shield, this electromagnetic interference, or EMI, would blast through the vehicle, scrambling low-voltage sensors, the infotainment screen, and even autonomous driving systems. But to work, that shield must be perfectly grounded 360 degrees around the connector casing. If that grounding fails, the whole cable acts like a giant, disruptive antenna, actually routing these cables through a tightly packed vehicle chassis is a packaging nightmare. These thick copper cables are stiff. You can't just bend them at sharp 90-degree angles. Engineers have to calculate strict minimum bend radii. Bend it too tightly, and you crush the internal insulation and stretch the shielding, creating exactly the kind of micro-fractures and heat buildup we talked about at the start. They also have to be routed away from sharp metal edges, suspension movement, and extreme heat zones, often requiring secondary corrugated armor to prevent chafing over hundreds of thousands of miles. Before a single harness goes into a car, it undergoes HIPOT testing, blasting it with thousands of volts to ensure there are zero microscopic leaks in the insulation. So, the next time you look under the hood of an EV and see those thick orange cables, you'll know exactly how much engineering is keeping that immense power safely contained. If you want to understand more about the systems powering the future of mobility, make sure to like, subscribe, and stay tuned to Vidyut Tales.